give the report. The talk is in front of other mentors and mentees. Yes, so it's open for others to join as well. And and just to reiterate, you do not have to give a talk, but if you feel like you want to, please, submit the abstract and title by today, I guess. Yeah, today's August 4th. Yeah, by today, so we can get the schedule in. For and then for so I see someone just asked if about assignments or lecture notes. The lecture notes are on the Dropbox that is for this nuclear physics mentor program. I'm not sure exactly when you joined, but we can try to send another email out with the link to the Dropbox. For the reports, we recommend that you do a weekly report over what you have learned that week from the lectures that are given, do some exercises. That one's up to you, based on, since there's a wide variety of people with different levels. You whatever you feel comfortable discussing, if it's just a couple paragraphs, if it's doing some calculations, that's up to you. Those are optional, but highly encouraged, because you can essentially consolidate all those into your final report, or at least they can make up a portion of your final report. So it's to help you get to the final report. And then the lecture notes from the lectures are also on the Dropbox in their folders. My lectures today will be put up there after the talk. Someone else asked about the certificate. To get the certificate, you have to submit the report. You do not need to give a talk. So the talk is bonus if you feel like it. So just again, if you will get the certificate by submitting just the final report. No other there's no other requirements from our side. Giving a talk or doing these extra optional exercises is up to you if you want to do them. All right. So we should, and I see one more question. Final reports can be given for each course or as a whole. That's a good question. I'm not sure. One of the admins may need to answer this, but I was under the impression it was for each of the courses. So like for the nuclear physics mentor program, we want a final report, up to 5 pages. You don't need to go more than that, or, of the material from the nuclear physics mentor program. But double check with the REYES admin, and I'll try to do the same and make sure that information is given. What should be included? So as we said in the emails, this is up to you. It's covering your experiences with the program, what you've learned, and just a cohesive report. So we're not going to, there's no strict requirements other than, maximum 5 pages and just on the material that you have covered, learned, experienced during this program. All right, we probably should get started with the lecture proper, as there is quite a bit today. I see one more question. How do we submit the final report? In Dropbox for us. And please label it as as the final report. So let's get started. You have, the host needs to enable sharing for me. Please, Jeff, if I can share my screen. So far you've seen a few different lectures on different aspects of nuclear physics. And I'm going to continue with the discussion with an application on some stuff that Wyatt discussed last week on reaction theory. So let me share my screen. All right. Oh, I see there's another Q&A. As I mentioned, the reports are due by August 18th. So I'm going to discuss an application of nuclear physics in reaction theory, and really just trying to apply some of the stuff that you may have learned about in for a case study of neutrons and protons interacting with each other. There's quite a bit here, and I'm only giving one lecture on this. Next week, Tommaso will be giving a lecture on some aspects on the structure of nuclei. So we may skip a couple of the more mathy details, but I'll make sure everything's in the presentation for you so you can look at it at your leisure. So kind of the general overview is I want to discuss kind of why nuclear reactions are important and looking at a specific case, and some basic aspects of applying reaction theory to nuclear reactions, which is just looking at the kinematics of say a proton and neutrons scattering off each other. How do we quantify scattering? And we do this with probability amplitudes. Finding out properties of the interaction and scattering processes through something we call spectroscopy, which is studying the masses and lifetimes of particles which are formed by interactions, and then looking at the specific case of neutrons and protons and how they form the deuteron. So let's start off. In nuclear physics, many of the phenomena we observe are driven by nuclear reactions. And a simple example that we're all familiar with is the sun, which fuses elements to heavier elements and releases energy. And in the kind of one of the simplest reactions is the proton-proton fusion chain, where you have two protons coming in, they interact and fuse to form a deuteron, which is a neutron-proton system that's bound, that we will focus our discussion on. That deuteron then interacts with another proton to form a helium-3 nucleus, which interacts with another helium-3 nucleus to create helium-4 and an excess proton. And all these processes release energy, and this is how the sun fuses to form energy and releases energy in the form of light. So these nuclear processes are very fundamental towards a lot of things we see. And as nuclear physicists, we want to study these aspects to try to get a quantitative understanding of how these reactions work. And how do we do that on Earth, let's say? Well, we study these types of reactions in accelerators or colliders. And here I have a little cartoon of what an experiment is from a theorist perspective. You have some beam of particles which you shoot at a target. In this case, you can think of this as a neutron, and this can be a proton. And then once they interact, you have a bunch of detectors that detect the reaction products and send some information to some computers. These reaction events are measured, and this is what I call N here. These events are measured by experimentalists and transformed using the parameters of the experiment itself to something called a cross-section, which is a measure of the probability of the rate of reaction that can occur. And this is related to a theoretical object, which is called the reaction probability amplitude. These are all quantum mechanical systems. You may have heard that quantum mechanics is probabilistic in nature, and that is just a fact of how quantum mechanics works. And so the link between experiment and theory is given by this relationship, where you measure the number of events, relate that to a reaction rate, which then you relate to a probability amplitude, which is a mathematical object that we want to either constrain or predict from some fundamental theories. And so what happens is these reactions happen, and then we collect events. These detectors are collecting different events. Some signals are sent to a computer for processing and analyses, and we get this information, the counts of this experiment, to then relate to this reaction process. If the interactions are sufficiently attractive, particles can form what are called bound states, which are systems that that combine together to form new particles. And this is, this whole E equals MC squared business. You can, at some energy scales, you can create particles by binding or production. And in this example here, you have two particles binding together to form a stable state, which, can live for however long it lives. And then maybe it subsequently decays if it doesn't live very long, or in some cases, they can live forever. And this is kind of the basis of everything we see in matter. If we look at kind of the lightest nuclei, here I draw in this dark gray neutron, and then this red a proton, and the light nuclei, helium, lithium, so on and so forth, are all formed by the binding of protons and neutrons. And there's different nuclei you can form. They can either live forever, as is in this kind of light gray background. These are elements that live forever. They can decay various different processes. These elements here will emit a proton. These elements here will emit a neutron. These here will decay via beta decay, which is just the emission of electrons to transform the neutron into a proton. And then some of these elements which you think you can form actually are not stable at all, and you can't form them. So understanding the patterns of nuclear interactions through reaction mechanisms is how we understand kind of the building blocks of matter. So these atomic nuclei are bound states of protons and neutrons. We want to study atomic nuclei through nuclear reactions. The simplest one we can focus on is the deuteron, which is a bound state of a proton and a neutron. So this is the simplest nucleus. We're going to use reaction theory to gain some understanding of the various properties of the deuteron using some of the techniques that Wyatt introduced you in the past 2 weeks, and also Vincent in the weeks before. The deuteron is often called the hydrogen atom of nuclear physics, as it's a kind of the simplest structure that can exist, and it's useful for studying the nature of nuclear forces between two bodies, i.e. the proton and the neutron. So some of the things that we would like to understand is the properties of this deuteron, like what is its mass, what's its lifetime, what's its spin. If you're familiar with quantum mechanics, particles can have what are called spins, which is like a little spinning top, but in a quantum mechanical sense. I won't go into the details about that here. I'll let you read about that offline. What's its radius, what's its charge, so on and so forth. So we want to understand these basic properties. Can we do that with reactions? And at first it may seem like, well, how do you do that? If we look at an example of what low energy neutron proton reactions look like, so this is the cross section, which remember is this reaction rate of neutrons hitting a proton, and it's a function of the kinetic energy of the neutron, right? So this is measured in kiloelectron volts, which is a measurement of energy. If you've taken some elementary physics in your undergraduate courses, you may be familiar with it, but it's just a measure of energy. So it's how fast the neutron's moving. We're looking at low energy, so it's not moving too fast, not at relativistic regimes. And the cross-section, experimental data points are given by these blue points here. And this red line is a theory fit, which I'm going to explain how we got this theory fit from, basic scattering reaction theory principles, and comparing this to the data. And so you see some features of the data. It starts off relatively constant. The unit of cross-section is what's called barns, which Vincent introduced. And as the energy goes up, the cross-section goes down. So this just means that the reaction rate for very low energies is pretty constant. But then as the energies move up, then the reaction rate starts going down. So hidden inside this cross-section data is information about the binding of protons and neutrons. And we're going to exploit these basic principles of reaction theory to get at what that interaction is and find this deuteron particle. So the big question is, how do we convert this experimental data to properties of the deuteron? So let's focus on some basic kinematics first, just to define our terms. I'm going to work in units. Maybe you've been introduced to it, but particle nuclear physicists often work in units where h bar, the quantum constant, and c, the speed of light, are equal to 1. It just makes it's useful so you don't have a bunch of numbers that are like 10 to the minus 30, blah, blah, blah. So here I'm going to define a nucleon, which is an object that can either be a proton or a neutron. So protons and neutrons are very, very similar. One is charged, one is not charged, sure, but let's kind of ignore the electromagnetic effects. The masses are really, really similar. So we're going to lump up these two objects into what's called a nucleon, which is very common to do if you're looking at kind of gross first approximation information and not trying to do precision differences. So in order to make life simple, I'm gonna say that the proton and neutron mass is exactly the same, and I'm going to call this the nucleon mass, which is about 940 MeV. So this is mega electron volts. Really, there is a slight difference between these two, but let's ignore those slight differences, and we're just approximately 940, just first approximation. As physicists, we often do approximations first and then do finer tunings on top of this. The nucleon itself will be moving with some momentum. We will use P to denote the momentum, and it has some energy. Instead of using E, I'm going to use omega to refer to the energy. If you're familiar with quantum mechanics, there's a fundamental link between energies and angular frequencies of objects like photons and also particles as well. I'm going to use omega here to denote the energy of the nucleon, because I'm going to use E for something else later on, so I don't want to confuse notation. And we're going to use Einstein's relativistic energy formula, because although we're looking at low energies, we're going to do things as if we can do it for any energy. And the energy of the proton then is the square root of the mass of the nucleon plus the momentum squared. And if momentum goes to 0, then the energy is equal to the mass, and c squared is equal to 1 here, so E equals mc squared. This is just the generalization of it. In the non-relativistic limit, so let's say you are really interested in low energies, then the energy is equal to the mass plus p squared over 2m. And this may seem familiar from your classical mechanics or non-relativistic quantum mechanics if you've taken these subjects. This is just the non-relativistic kinetic energy. So I'm going to define also the kinetic energy as T, which is going to be just the total energy minus the mass of the particle. This will make use of later. As an exercise for you, one thing you can do is take the general expression here and prove this expression. If you're familiar with Taylor series, that's how you go about to do this exercise. And again, these exercises aren't mandatory. These are suggested if you feel inclined. So we've described what a nucleon is. For reactions, we have two particles, two nucleons, a proton and a neutron. We will denote the total energy of a proton and neutron system by E, and it's going to be the sum of the individual energies. So here you have the sum of the two energies. And for convenience, we're going to introduce the total momentum of the two particle system, which I'm going to label as capital P, right? So neutron has particle, the neutron has momentum P1, the proton has momentum P2, and the total momentum is P, capital P, which is just P1 plus P2. To describe some useful kinematics, we're going to make use of the fact that we can value that coordinate systems are man-made objects, so we can choose whatever coordinate system we want to work in. I'm going to choose a coordinate system where the total momentum is 0. This is called the center of momentum frame. Sometimes it's also called the center of mass frame. In non-relativistic physics, it means the same thing. In relativistic physics, there technically is a difference, but for our purposes, call it center of mass. It doesn't really matter. In this frame, our total energy simplifies because now E is just twice the energy of one particle. I'm going to put these little stars on these kinematic variables to indicate it's the center of mass, center of momentum frame. And then this, all the is that the neutron and proton are moving back to back, which means then that their momenta are equal and opposite, right? So P1, I'm going to call it Q for convenience, and P2 is going to be just minus Q. So you see here then the total energy is just twice the individual energies of the nucleon. You can take this then, and let's say you want, so this is the energy, the total energy in terms of momentum. If you want the momentum in terms of the total energy, then you can just invert this relationship to find what Q is in terms of E. And sometimes we want to do that depending on what variables you want to scan. And some exercises show these relationships here, and make a plot using your favorite plotting software, Python, MATLAB, whatever, to plot the momentum as a function of the energy. I'm going to skip this section because this is kind of goes in detail, but I have it here in case you're interested for later, kind of some of the this background information. Often when we think about two particles, we think about what available energies or kinematic configurations they can have. We give that quantity a name called phase space. This is how you rigorously define it. The main thing here I want to point out is just you get some kinematic factor, which I call rho here, which is just proportional to the momentum and inversely proportional to the energy. This factor comes up over and over again. It's a measure of the available momentum space configuration the two particles can have. So ignore all this fancy math. You know, this is the main thing. It's just some kinematic factor. And, you know, as a challenging exercise, you can derive this as a simple exercise. Just plot this function. You know what Q is as a function of E. You can plot this rho kinematic phase space function as a function of E. All right, so that's how two particles work. We have energy and momenta. Now we want to make them react. So you have this binary reaction. We have a proton and neutron coming in with some initial configuration, and it evolves to some final configuration. How do we describe this reaction? Well, I'm going to, again, work in this center of momentum frame, and we can have these two particles coming in with initial relative momentum, Qi and minus Qi. They interact, and then they go off with some QF and minus QF, all right? The angle that the final system emerges from the initial system is called the scattering angle, right? So you imagine, you know, you have a neutron coming to hit a proton, and the neutron flies off at some recoil angle. This is the scattering angle, right? So those are our kinematics. And again, because we're dealing with this simple system, you get some nice conservation laws. Total energy is conserved, total momentum is conserved. So instead of writing EI, EF, PI, PF everywhere, we're just going to write everything in terms of E and P, since these total quantities are conserved. And this means, again, that you get this relationship coming out relating the total energy and the relative momentum. And again, an exercise, you can show these results. It's just based upon the previous work and then assuming that energy and momentum are conserved, which is true in this reaction. You can also work in a different reference frame. I only point this out because the data we have is not in the center of momentum frame. The data we have is you have a proton, a stationary proton in the form of hydrogen gas, and it's being hit by neutrons. And in this frame, this is often called a lab frame, where the actual laboratory experiment is happening. And the kinematics here are a little bit more complicated, but the point here is that if you have what you now would want is the kinetic energy of the neutron. The kinetic energy of the neutron is related to that relative momentum Q via this relationship here. An exercise is to prove this. This is kind of challenging, so don't get frustrated with it. But if you feel like you want to give it a try, relate it. But just so you know, the kinetic energy of the neutron is related to this relative momentum of the neutron by this relationship here. All right. So that's the kinematics. Now, how do we quantify based on those kinematics? Well, these are subatomic particles, so you need quantum mechanics to properly describe the physics. We can only describe the probability of an event to occur. And the way quantum mechanics does that is through what are called probability amplitudes. So your wave function for a particle as a function of the position and time is some amplitude of some wave, probability wave moving. And then to get observables, the probability of this wave function is simply the modulus squared of the wave function, and you integrate over all the positions of interest. These wave functions are complex numbers, so we have to deal in the world of complex numbers. We don't have that much time to review all of these intricate details. I'll just do a brief survey of it. But this modulus operator here is taking the complex conjugate of the wave function and multiplying it by itself. So just as a quick refresher, complex numbers have various representations. We often write z as x plus iy as a complex number. I is the imaginary unit, which is the square root of -1. The complex conjugation, all that does is flip the sign on the imaginary component. And you can get out the real and the imaginary parts separately by doing various operations. There's algebraic relations. I'll skip this, leave it for you. And there's also what are called polar representations, which instead of writing it as an x and y, you write it as a radius and an angle. So a complex number can be represented as some radius times some phase. And the components in terms of, say, the x and y are given by the usual trigonometric relationships here. And one of the useful identities to use is the Euler identity, where e to the I phi, where phi is this angle, is cosine phi plus I sine phi. And then you may know this, that e to the I pi is -1, very famous relationship. So from there's other operations you can do to isolate the magnitude and phase directly from the Cartesian representation. Here's a suggested exercise if you are not too familiar with complex numbers, how to get at some of these features here. All right, so we're going to use complex numbers, and because these are quantum mechanical systems. How do we describe reactions in quantum mechanics? We describe it in this fashion here. We have some initial state, so your proton and neutrons coming in together. There is some probability amplitude, which I call S here, that exists in order to evolve the system to some final state. So the final state is the outgoing proton and neutron. This S here, which is the scattering probability amplitude, is the probability amplitude for the system to go from some initial state to some final state. The scattering probability amplitude depends on the energy of the system and the scattering angle of the system. And then once you have the scattering amplitude, then the probability for the initial state to evolve to some final state is given by the modulus of S squared. So this is just as just in the typical definitions of wave functions for quantum mechanics. And then this probability here is related to that cross section that I showed earlier, which I won't go through the details right now. So one of the things that we can do to make this simpler is to exploit rotational symmetry. And if you're familiar with the hydrogen atom that you usually see in introductory quantum mechanics or modern physics or even in chemistry, is you use rotational symmetry to break up your interaction into orbitals, angular momentum orbitals. So in this case here, you have the neutron and proton interacting in some sort of quasi-bound state. There's some angular momentum, and quantum mechanics tells you that it's quantized. And because of that, we can break up the probability amplitude for the scattering to occur into different orbitals. So here is the S wave orbital, this is the P wave orbital, this is the D wave orbital, which may seem familiar from chemistry or quantum mechanics. They're both, it's both the same thing. And these orbitals are just telling you how much angular momentum each of these probability amplitudes are in. So the S wave is L equals 0, the P wave is L equals 1, and the D wave is L equals 2, and so on and so forth. Mathematically, it's given by this expression down here, where this P here is the Legendre function, which is giving you the shape of these different orbitals here. So we're going to use rotational symmetry to break this thing up into an infinite number of orbitals. And we're going to use the fact that at low energies, the dominant interaction is this one here. All right. So the dominant interaction is when there is, no excited orbital state. It's just a simple isotropic interaction. This is usually very good for low energies. At high energies, these things start contributing, but we're not going that high in energy today. So from now on, I'm going to just focus on just the S wave case, which means that there is no angular dependence. So I'm going to drop the angular dependence. And furthermore, because I'm only going to consider the low energies, I'm going to drop the subscript 0 just to save notation. But we're working in this approximation here. So we can do one step further. When you have two particles that are coming close together, there is a probability that they don't interact at all. If we're trying to study reactions, that case is not very interesting. So we want to remove it. So we will write this scattering probability amplitude as equal to 1, which is the case when there's no scattering, right? If there's no scattering at all, the initial state is the same as the final state. So this is just the identity. Plus 2i rho times m. So what is all this? 2i is just a convention that we use in reaction theory. I is the complex unit, the square root of -1, and 2 is just convenient factor to cancel out some 2's later on. But this is purely convention. You can redefine this without the 2i's if you so choose. Rho here is this kinematic phase space factor I glossed through earlier, just telling you how much available energy space this system has to play with. And m here is now the reaction amplitude that actually encodes reactions. We generally call this thing the scattering amplitude. This is the amplitude for some scattering to happen. It doesn't have the case where there's no scattering. And so this encodes all the dynamics we want. And in practice, then that cross section that I brought up before is actually proportional to the modulus of m squared, right? So this is that scattering amplitude, which is related to the cross section. The scattering amplitude is related to this probability amplitude, which is the probability of some initial state to evolve to some final state. So we've done all this work to define what this thing is in terms of basic quantum mechanical properties. What more can we do with this m? Well, we're going to use the fact that this is quantum mechanics, so everything is probability, as we said. Oops. This Zoom thing is in the way. And the total probability for any initial system to go into any single final system you want has to be 1. So if you sum up over all the different types of reactions that can occur, the probability has to be 1, because we expect probability to be conserved. That enforces, if you apply this to our definitions of this S probability amplitude, probability of I to F is this here. This implies then, for this one final state, since we're just dealing with neutrons, protons going to neutrons and protons, that the modulus of S squared is equal to 1. All right. So this is a constraint now on the probability amplitude. Furthermore, in terms of the scattering amplitude, one can show, if you take this expression and plug our expression in terms of the scattering amplitude into it, you can arrive at what's called the unitarity condition. So unitarity is a fancy name for probability conserving, which just means this condition here. And this is the unitarity condition for the scattering amplitude. So the imaginary part of m is constrained to be this kinematic phase space times the modulus of m squared. I won't go through the derivation. It's an exercise to do it. All you do is you take this expression, plug this into here, and simplify it down and use your complex arithmetic rules. All right, so why is this condition useful? Well, if we fix the energy, let's say we're going to have this reaction at 10 MeV. At that fixed energy, the amplitude needs 2 real numbers in order to completely describe the amplitude. Remember, with complex numbers, you have a real part plus I times the imaginary part. Well, unitarity relates the imaginary part with the real part and the imaginary part. So this just means then that you have a constraint where instead of instead of 2 real numbers to constrain the amplitude, you only actually need 1. And that's very nice, because the less, the less things we have to constrain or describe, the more predictive power we have and the more analyzing power we have in order to describe our reaction system. Yeah, so here we're going to use this constraint allows us to restrict how many parameters we need to use in order to describe the neutron proton reaction. Note that from complex arithmetic rules, you can rewrite this condition for the imaginary part of M as the imaginary part of the reciprocal of M, and this is in terms of minus rho. So again, this thing here is a completely known function. It's the kinematics of the reaction, and this dynamical quantity, the imaginary part of its reciprocal, is completely fixed by kinematics. This means that we can parameterize the reciprocal of M in terms of one real number, just as we argued up here. And the reciprocal of M is equal to what I'm going to call the reciprocal of the K matrix minus I times rho. And the condition here is that this thing must be real. So this encodes the actual dynamics. This is just kinematics. And just by inspection, if you take the imaginary part of this, this is real. So this contributes no imaginary part. So it's minus rho. So it satisfies this condition. It's a good representation. And instead of parameterizing M, we need to parameterize K, which, parameterizing a simpler object is very nice. I see there's a Q&A. Yes, I will. The lecture notes will be put online, and we'll send an email out. All right. So an exercise is to show this relationship here. All right. So the goal is that we need to describe this thing here. We can write it in terms of this. We know this function, so we need to describe this function. And that's the goal that we want to do. There's an alternative way to think about this, which we will make use of, is that instead of using the Cartesian representation, we will use the polar representation. So here, M will be the magnitude times this phase factor here. Now, here you need to know two real numbers, the magnitude of M and the phase of M, but because of this constraint, you can show, and this is going to be an exercise, that M here can be written in terms of this phase shift instead. So 1 over rho, which is known, times this exponential to the I delta times sine delta. And delta is this real number that we don't know as a function of energy. So you can either have one real parameter in terms of the K matrix or one real parameter in terms of the phase shift. Both are often used in reaction theory, and they are obviously linked together. And one of the things here is to show that the reciprocal of the K matrix is equal to rho times cotangent delta. So that's an exercise. So now that we've reduced our problem to a simpler function, what more can we do? Well, if we're looking at low energies, we can think about using Taylor expansions in low energy. An alternative way to think about low energy is low momentum. Recall that energy and momentum are related by that square root relation. So I'm going to express the reciprocal of the K matrix, or more truthfully, Q times the cotangent of delta as a Taylor expansion in Q. And I won't go through the details of how you go about this, but this is essentially just using a couple properties of scattering amplitudes and Taylor expanding in the momentum. One can show this type of form, and if you've taken quantum introductory quantum mechanics and covered introductory scattering, you may have seen some of these things before. The leading order term is written in this funny way, but there's a reason for it. And this leading order term, this A here, is called the scattering length, which effectively is telling you about the strength of the interaction. And this R here, which is a factor from the next to leading order term, is related to the range of interaction. So it's written in this funny way to link up to what you learn in non-relativistic quantum scattering, how these A's and R's come about. But we can just take this as kind of given right now. So instead of so we're going to parameterize our phase shift or the K matrix in terms of this Taylor expansion, where we want to determine what the strength of interaction is, the scattering length, and determine what the effective range is, this range of interaction. Once we determine those, we start to describe the reaction in terms of its strength and its effective range, and then we can use those properties to determine properties of the deuteron. All right. Let's skip that here. That's exercises for you. All right. So where are we at so far? We have the data for neutron-proton scattering. The data is given in terms of cross sections, which is related to the scattering amplitude. We have just written the scattering amplitude as a function of real parameters A and R plus some kinematic variables. And so we want to parameterize this A and R and fit this to the data to learn about what A and R are. But once we do that, how do we get to properties of bound states? So if we do protons and neutrons interacting, how do we get properties of the deuteron based upon this thing? Well, here's just a quick introduction to how we do that. So there's a deep connection between scattering and bound states. And I'm going to use a fancy term from complex analysis. They are pole singularities. What does this actually mean? Well, this means that when the scattering amplitude is near the energies where this bound state can form, the scattering amplitude has this form where it's essentially a 1 over x form. So 1 over x, as x goes to 0, diverges to infinity. That's a signature of a bound state. Here it's 1 over this expression here. When the energy hits this expression here, the amplitude diverges. I won't prove this, but when you take quantum mechanics, you'll see this for the hydrogen atom, something similar happens there. So I'm just stating this as fact, right? So this is a bunch of facts of how this all works. So the scattering amplitude itself will blow up when you get near a bound state. So when the proton neutron have enough energy to start binding itself, the amplitude will diverge. And it can be parameterized this way, where capital M here is the mass of the hadron that has been formed from the binding. And this gamma here is related to its lifetime. So the lifetime is 1 over this gamma here, which is what's called the decay width, just for your reference. And it's divided by 2 just by some convention. So what's interesting here is that for states that have a long lifetime, for states that have a finite lifetime, the lifetime is finite. So this gamma here is a non-zero number, and when the energy hits this complex number here, you're going to get this divergence to occur. Well, you can't have complex energies. Yeah, in physics, you can't have complex energies, but you can extrapolate to there based upon some model to see some behaviors of the amplitude. Why it may have touched upon this briefly, but I'm not going to touch about from that here. Particles which live forever, so tau goes to infinity. That means this decay width is 0. That means it's real energies that this thing can form. And in this little cartoon of the energy plane, it's going to be some divergence in the energy. So in order to find where the amplitude diverges, what we do is we look for where the reciprocal of the amplitude goes to 0. Since, when 1 over x goes to infinity, that means x goes to 0. So to find this location, we just look for the where the denominator goes to 0, and that gives us information about the bound state. So in this example here, in the exercise to show that the amplitude can be written in this form based upon the earlier relations. If a bound state will occur when this denominator goes to 0, so this means Q cotangent delta is equal to IQ. And if we assume that the scattering length is greater than 0, which is the case for the situation we're dealing with, then assuming only a leading order effective range, so let's assume R is 0, Q cotangent delta is -1 over A from the expression that we have. This means here that we can define essentially a complex version of the momentum called the binding momentum, and the energy of this bound state is going to be equal to twice times the square root of the mass squared minus the binding momentum squared. So what does this mean? This means that some of the energy Oh, oops, I'm going too far. So this means then for that simple effective range expansion that we did, the decay width will be 0, and the mass of the bound state will be given by this relationship here. So what's actually happened physically, what's going on is that you get a stable bound state for this A is greater than 0. And what this means is that if this location is the neutron plus the proton mass, some of the energy has been taken from the proton and neutron to bind to form the deuteron. All right. So this difference between the mass of the deuteron and the proton neutron mass is called the binding energy. So that's how much energy you would need to hit a deuteron with to break it up into its proton and neutron constituents. All right. So I'm sorry I'm kind of flying through this, but I'm trying to get through this in this hour time slot. The final thing to discuss is the applications to neutron and proton scattering. So again, to recap, we have reaction rates that we can measure from experiment of neutron proton scattering. We can relate this to some theoretical model for the scattering amplitude in terms of some parameters, the scattering length effective range, which tells us something physical. And from the scattering amplitude itself, we can determine the bound state, mass, and decay width from them looking at the zeros of the reciprocal. So we want to apply this to neutron proton scattering. There's one little caveat with neutron and proton scattering, which I feel the need to cover just so you're aware of it. So protons and neutrons, nucleons themselves have spin angular momentum. They're like little spinning tops. The strong interaction between protons and neutrons, nuclear forces, can and does depend on the spin degrees of freedom. So in addition to the orbitals, you also have, so you have orbital angular momentum, you also have the spin angular momentum. And the interaction does depend on this. So a nucleon can either be plus 1/2 spin or minus 1/2 spin. Remember, I'm working in this units where h bar is equal to 1. So if you're taking quantum mechanics, h bar over 2 is a spin 1/2 degree of freedom. And the nucleon itself is a spin 1/2 degree of freedom, and it can either be plus 1/2 or minus 1/2. When you have two nucleons, there's different combinations you can make. You can make where either both the neutron and proton are positive spin 1/2, both the proton and neutron are negative spin 1/2, or both the proton and neutron are spin 0. So this means plus 1/2 is spin 1, minus 1/2 is spin -1, or plus 1/2 minus 1/2 is spin 0. So they can either be 1 or 0. It can be 0 in two different ways, however. This is just from the weirdness of quantum mechanics. They can either cancel each other out symmetrically or cancel each other out of phase or asymmetrically. So since both the spin ups and both the spin downs are symmetric combinations, we will wrap up this spin 0 symmetric combination to here. So this is all part of the spin 1 multiplet or spin 1 collection. This here is by itself. This is definitely spin 0. And these are the different cases you can have. So you have 4 different cases, either spin 1 or spin 0. So the cross section then is going to be a weighted sum of these 2 different cross sections. We call the spin 0 a singlet case because there's only one option for singlet. And we call the spin 1 case spin triplet as there's 3 different options. So the weighted sum is 1/4 spin singlet plus 3/4 spin triplet. And the quarter comes, or the 4 comes from, there's 4 different spin states, and the relative weight, there's 1 spin singlet state and 3 spin triplet states. All right. So that's a little caveat. If we want to do this analysis correctly, we have to take into account these effects. And in fact, it's the reverse of this that happened historically. They had some predictions for what the scattering amplitude would look like, not including spin effects, and they found the cross-section and theoretical predictions disagreed by a good amount, and that's what led to them thinking about, oh, there's spin degrees of freedom here. So we're doing it from knowing that case instead of historically. So we have enough tools now to analyze the data. We have these cross sections here. Each of these cross sections, which I write in terms of X here, so X can either be the spin singlet case or spin triplet case. In terms of the amplitude, this is the exact normalization of the amplitude. I won't derive it here, but you can look in textbooks to see how it's derived. And the amplitude we wrote in terms of the phase shift. And the phase shift we wrote in terms of this A and R parameter. So the low energy parameterization, if you plug in all these expressions into the sigmas, it's an exercise for you. The cross section itself is equal to 4 pi divided by this denominator here, where A of x and R of x are the scattering length and effective ranges, and x can be either the S or T, so you have to add up both combinations here. And Q here can be written in terms of the neutron kinetic energy. So you can write a little Python script, which is what I did for this here, to generate this function and fit it to this data, which data just comes from some online resource. And what I find from my simple fit parameters, there's some kind of conversions between different units. Here I'm presenting things in terms of Fermis, which is 10 to the minus 15 meters. It's a femtometer. And I can fit this to data, so the experimental data minus the theory using a chi-squared fit. I find these various parameters for the effective ranges and scattering lengths. These may not mean too much to you, but if you study nuclear physics in this very simple fit, if we compare it to, it's a little under a decade old now, or no, it's a little older than that, over a decade old now, but some a detailed analysis of this, and I invite you to look up this paper. The numbers I achieved here with this very simple fit agree with a more precise determination of these things here. So this is in the ballpark of being a good description of this data with all the assumptions that we've made. So now that we have the scattering length and effective ranges, what can we do? And one exercise here is to take your favorite programming language, take my numbers, and make this plot of the cross section. And see how it looks. So I'm going to focus on one of the case, the spin triplet results from my simple fit. We have this. I'm going to search for the poles of the amplitude, or where the inverse amplitude goes to 0. So this is solving this quadratic equation for Q, which I can write Q in terms of the energy. I'll let you do that. But for my numbers here, we find that the deuteron lives forever, right? So it's got a long lifetime. It's got a binding energy of 2.1 MeV, and the mass of the deuteron is about 1878 MeV. So if we compare that to kind of the best analyses, the binding energy is 2.224 MeV, so I'm in the ballpark correct here. All right. So, from the simple analysis, it looks like we're getting a description of the binding of protons and neutrons to form a deuteron, which is very exciting. And some exercises here. So what have we learned? The deuteron, we've learned some properties of the deuteron with its masses, with its binding energy, its lifetime, and some other quantum numbers associated with it. I don't have time to go through the details now, but just to say that I apologize for going through this quickly, but I wanted to, this is kind of condensed down from what I was originally planning to do, since I'm not giving a lecture next week. But in general, this is an application of a lot of the tools you've seen so far in this to do what's called spectroscopy, which is understanding the properties of bound states coming from proton-neutron interactions, and using very simple techniques from reaction theory, and some simple in quotes, because there's a lot more we can do here, but using kind of a first pass approach to this, we can actually get at some properties of nuclear binding from reaction theory itself. So let me end here. Let me say that I'll put these slides up online on the Dropbox and for everyone to see. All right, so I'm sorry I know there's a next section ahead of me, but are there any quick questions I can try to answer? On the slides, my email address, or you may already have my email address now, is on, so you can always email me if there's further questions. All right, well, if there's no questions, then I thank you very much for attending. I hope you have a good rest of your day and weekend. And I think the Python for STEM people are coming up next. Oh, I see some question. Will linear algebra serve as a sufficient prerequisite to learn basics of group theory? Yes. So linear algebra is a necessary kind of background information to understanding basics of group theory. And usually in an undergraduate course, linear algebra is usually a requirement for physics degrees. If it's not, I definitely take it. It's a indispensable tool. All right. Are there any other questions? All right. Doesn't look like it. So thank you very much. And I think the Python group is next, right?